afternoon. You're here on ThinkTech Hawaii with research in Manoa, and I'm guest host Ethan Allen, filling in for Jay Fidel. With me today in the ThinkTech studio is Jeff Gillis-Davis from the, now if I'm getting this right, the Hawaii Institute of Geophysics and Planetary Science?
Yeah, HIGP for short, a lot easier to say. So
HIGP.
yeah, we're in at UH Manoa.
Okay, and you study Earth processes and planets, basically.
Mostly I study planetary processes.
Okay.
So I grew up studying the moon, how it formed, evolved, what the different surface types are. I also study Mercury, and now even study asteroids and the meteorites that come from asteroids.
Oh, okay, so you're expanding your range all the time.
Yep.
Excellent, excellent. Well, this is great, and it's interesting. You've got an idea that we should be studying the moon very closely, and indeed actually sending people to the moon, right, to study it. Really up close and personal.
Up close and personal, and it's, you know, the nearest rock to us, so it makes a great place to kind of go out. It's in our backyard to start camping and see what's there so that we could use it and then maybe step from the moon out to other asteroids, maybe onto Mars or other interesting places in the solar system.
Right, because if we're going to do this kind of stuff in a big way, you've got to start somewhere, and it's certainly the logical place to start, right?
Yeah, that's my logic. Maybe not everyone's logic, but definitely mine.
Oh, and it's wonderful. It's close in, relatively. We know we can get there because we've been there before.
Yep.
It's been a surprisingly long time, right, since anyone set foot on the moon.
It has. It's just past the 46th one-month anniversary of Apollo 11 landing.
Wow.
And then we had, you know, 5 more landings after that, and we haven't been back since 1972 with a human mission. We have a mission going around the moon right now called the Lunar Reconnaissance Orbiter, and it's been up there for about 5 years orbiting and mapping the moon, and it's doing a great job, and some of the data that we'll look at today is from that mission probe.
Excellent, excellent. So I know some people would say, and I'll be play a little devil's advocate here, but some people would say, you know, why bother with this stuff? It's just a chunk of rock up there, you know?
Yeah, well, you know, some of the great things that came out of Apollo are the computers. You know, it took a house to get all those computers, you know, now that we have the computing process in our pockets. And that plus, you know, life support systems, it wasn't even dreamed about that you could actually measure someone's body temperature, heart rate, EKG, you know, when they were 250,000 miles away. And that's the standard thing when you go to an ICU now. So there's a lot of, you know, spin-offs that come out of the Apollo and the space program.
Sort of side benefits of doing a project like this, and that other technologies sort of fall out that then take lives of their own, basically.
Exactly, and you know, one of the things is you can't predict what those technologies will be.
Sure.
You just know to overcome that, you know, boundary, you have to make new technologies.
Right.
And
you have to have a focused project, like getting to the moon to give the driver, basically.
Right, it gives you that mission statement. This is what we're going to go do, and you know, we're going to do it, and these are the things we're going to need. And you know, people getting behind that mission. That's, you know, one of the things that made Apollo so successful.
Cool.
They weren't going to the moon to do science. They were going to the moon to beat the Russians. But by the way, hey, you know, we got a lot of great science, and we learned about our nearest neighbor. And it was quite shocking. One of the things, I think we have a slide, well, maybe even start with a refresher course.
Right.
You know, when we look at the moon at night, we see a dark surface and a bright surface. And if you'd call that image up, the dark areas are basaltic regions. So this is a volcanic material. It covers about 30% of the near side. And these are lava flows that came out, you know, about 3 to 4 billion years ago. So these are pretty old rocks. But the brighter areas, they have a lot less iron, so they're brighter. Those are even older. They're, you know, over 4 billion years old. So this is an ancient piece of crust. And it's been sitting there orbiting the Earth, collecting a lot of information that got lost here on Earth. We have, you know, plate tectonics and weathering and erosion. So our record is only, you know, a couple 100 million years old. Most anything older than that is now erased. It's gone down an ocean trench somewhere.
Right, right.
So going to the moon, we can study that early solar system, and we can learn, for one thing, the impacts. We're at a very big, important process. You look at the moon, and you see how many impact craters there are.
Right.
And even the biggest ones, if you look at those Mare areas, they're dark and they're circular. And for a while we thought that was impact melt, but it's actually a huge basin that made a bowl. And then afterwards, the volcanic eruptions filled that bowl, and that's why they look circular.
Oh, okay.
So, you know, stuff like that. The other thing was that the moon had a magma ocean, and that's what caused it to have a differentiated crust. And that's a standard idea now with the inner terrestrial planets, is that they probably all had a magma ocean. It's something we didn't understand, and probably plays an important role for beginning of plate tectonics.
Ah, okay, okay. So yeah, in a sense, you're saying the moon is sort of like an archive of
It is.
early solar system history, basically.
Right, and in some ways, an attic. And some people think that we could actually go back to the moon and collect very old Earth samples. If you collect samples here on the Earth that are 4 billion years old, they're really small, tiny rocks or mineral fragments. Well, one idea is that large impacts hit the Earth, blew material up that then got collected by the moon.
Right.
And those rocks could be there. Very small percentage, very low probability, but possible.
Right. This is why, again, you'd want some significant exploration on the moon, right? And you have to do a lot of sampling to hit one of those rocks, presumably.
Exactly. But if you set up a system that would just be automated, it could just run, and an alarm goes off. You go look at the rocks and see what's there.
Huh. Cool. Cool. And now the moon is sort of it is interesting because our knowledge of it changes right over time. For when we were growing up, everyone always said there was no water on the moon, and now it's pretty standard. Yeah, there is water on the moon.
It's wet and getting wetter all the time.
Really?
Well, yeah, that was the idea back in the Apollo ages when we brought the samples back. They were dry under those circumstances. The instruments that we had a certain level of precision, and the amount of water that was there was below that level of precision. Now with better instruments, we can see that there's ppm level of water, similar to some of the driest volcanic rocks on Earth. And that's the internal. So there is a little bit of internal water, but it's also not uniform. Some of the rocks that we have from the interior are different than other rocks. So it tells us that the moon is very heterogeneous inside. And the next step is to figure out why that is, what caused it. But there's also water on the outside.
Right, the poles have.
At the poles, and that is one of the probably targets for the lunar bases. And we know there's water there from a couple different lines of evidence. There was Clementine radar data back in the 90s that bounced the radar signal off the polar region of the moon and was received here on Earth, and it had the characteristic signature that there was some water ice there. Since then, we've had Lunar Prospector, and it has collected data about hydrogen levels, and if you associate the hydrogen with water, there's 0.2, 0.4 weight percent water. Not a lot of water, but water there frozen as probably some kind of ice, dirt, or regolith mixture. We also have had the L-Cross impact, which happened in about 2010, where we took an upper stage of a rocket about the size of a bus and hit it into one of these craters that we thought might have volatiles. And then there was a shepherding spacecraft behind it that took the spectral data, the light bouncing off of the ejecta, and it showed that it had different volatiles, one of which was water, some CO2 ice as well, that was in that permanently shadowed region of the moon. So that was even stronger indication that there is water ice at these very particular regions on the moon.
Right, right. But again, it's good, a nice example of why you need to study this, because you're correcting these misimpressions that we have.
Yeah, there are always misconceptions. When I teach my class, I teach a 100-level geology class about the planets, and I tell them, by the end of this class, probably 5% of what I say will be, proven incorrect and that's by just the time of the end of the semester. And in your lifetimes, probably 20% of it will be shown to be incorrect, because that's one great thing about science, is that we're always rewriting the textbooks.
Right. Facts are actually rather transient things.
Yeah, yeah.
We used to actually do a professional development exercise where we had a 15-question true-false test, and we said to the teachers, if they finished taking it, this is very easy to score. 20 years ago, these questions were all true. Today, they're all false.
Yeah, so that's one thing I enjoy about doing science, is that there's always change, new insights.
Even with something as relatively sort of inert as the moon.
Exactly. A lot of people thought when we got to the moon it would just be a cold briquette, that had never had any geology on it. But since we brought back the rocks, we see there's a lot of important geology there, and how it relates to Earth and the other terrestrial planets.
Excellent, excellent. So what is the current theory about the formation of the moon? I mean, is it really, is that the big one that it's?
The big whack is the most preferred.
Okay.
So that's where something roughly the size of Mars, or roughly half the size of Earth, comes in on a glancing blow, ejects material off the Earth, and some of that then coalesces around the Earth and forms our moon today. 20 years from now, who knows? This theory is only about 20 years old, but it combines one, certain isotopes like oxygen isotopes between Earth and Moon match. So we know it probably came from that rough distance of 1 AU from the sun, and other instances like we know it's volatile poor. Although we've been talking about water, other volatiles like water are depleted in the moon. And its composition is roughly that of Earth's mantle. So it makes a good match that way. Some of the other theories were that something came by and was captured, or that the Earth started to spin really fast and a piece of it spun off, and that allowed the moon to form. But we think right now that the big whack is our best idea.
Good, good, okay. So now the moon is sort of unknown in some sense because the way it rotates around us, it has only one face facing us, so we never see the far side of the moon, right? Right,
that's true. So if I may use this.
Sure.
So I'm glad you said it does rotate. So, we start here. Here's the near side of the moon shown at Ethan. This would possibly be a full moon if the sun's on that side. So when it gets to the other side, in order for it to keep that face to you, it has to rotate.
Right.
Or else, when it got to that side, you'd be looking at the far side of the moon. So a common misconception there is that the dark side of the moon is the far side. The dark side's always changing.
Right.
Your day is about, a month long on the moon from sun up to the next sun up.
Right.
So if you're going to create or have a lunar base on the moon and you're near the equator, which is one of these difficulties, you have to survive that 2 weeks of night.
Right.
Which is frigid, minus 300 degrees Fahrenheit. So that's one reason why, a polar actual lunar base might be a better spot. So that if you're in an area where you're on a mountain, you could be potentially in eternal sunlight, and then use solar panels to create your energy. Your thermal regime would be very even, no big high fluctuations of 250 degrees Fahrenheit during the day and 300 degrees Fahrenheit at night. It would be very more stable and very much easier to engineer.
Excellent, excellent. Well, this sounds great, and I want to dig into it a little more deeply here. I think we need to take a brief break here,
okay.
And then when we come back, we'll continue our exploration. You're watching Research in Manoa. Guest host Ethan Allen here. Jeff Gillis-Davis from HIGP.
Manoa, HIGP. Great.
We'll be right back.
Aloha. My name is Josh Green. I'm a senator from the Big Island and the ER physician. Every other Tuesday, I get to host a show here on the ThinkTech program about healthcare. We call it Healthcare in Hawaii. It's really enjoyable for me to bring other healthcare leaders from around the state to talk about our pressing issues. Hawaii has long been the health state, but we need to keep up the momentum, the inertia, and with your help and with your participation, we can come and share all of the big issues that are pressing day to day. Thanks for joining us every Tuesday, alternating weeks from 2 to 2:45.
And you're back here on Research in Manoa. I'm your guest host, Ethan Allen, here on ThinkTech Hawaii. With me today in the ThinkTech studios is Jeff Gillis-Davis from the Hawaii Institute of Geophysics and Planetology, or Planet Science. And we're talking about the moon. We're talking about, actually about lunar bases and all. And we were earlier sort of going over some general geology. Now, we have actually been, of course, to the moon. We had a set of Apollo landings. I think you've got a slide here that shows some of those sites.
Okay, so this is a more basic step back. Again,
Okay.
We talked about the Maria and the Highlands. So if you go to, I think it's the next slide, slide 4. So these are the 6 Apollo landing sites that landed on the moon and brought samples back. And people, aren't aware how much they brought back. It's 800, almost 50 pounds of sample that are stored in Houston, Texas. As a PI, we get to write a proposal and request samples. You know, it's very hard to get, very competitive.
Sure.
But we have to, you know, say what kind of science we're going to do with it and how that will benefit the body of science. A lot of people are only aware of Apollo 11, and then, you know, after that, nothing happened. But we did land 6 times on the moon.
I noticed they're all sort of more or less, though, sort of temperate to tropical, as it were, on the moon.
Right, and that's one thing, you know, I wanted to bring out too, is that, you know, for safety reasons and for the mission design, the equatorial regions on the near side were really the only places that Apollo could get to. So in our next generation of spacecraft, you know, going potentially to the far side and studying the geology back there, we would have to have another orbital spacecraft so that we could communicate with that lander on the far side. But the polar regions are also a great unexplored area and very different than any of the Apollo landing sites with, again, the volatiles that we mentioned, the ability to look at the near side, but also to just sweep over the Terminator and go on to the far side and study, you know, one of the biggest bases, or the biggest basin in the solar system, which may be the first basin to mark this cataclysm that's recorded on, you know, the inner planets except for Earth, because we don't have that older crust.
Okay, well, that's great. I mean, that makes perfect sense, and I can sort of see why the polar regions would make a lot of sense for the next thing. Just out of curiosity, why weren't they done in the Apollo flights? Why did people avoid that? Is it trickier to get there?
It is trickier to get there. They would have to do what's known as a plane change. So when they come in around Earth, our moon orbit, they're coming in around the equator, so they can go up or down from 0 degrees, a little bit. But to go into a polar orbit, they'd have to change from going this way to going in a polar orbit.
Okay.
And that's, you know, a big energy penalty. And Apollo wasn't going to do that. And they weren't going to land on the far side for safety reasons.
Right.
So that's why they limited to only those near side spots.
Cool. So I guess the next question is, all right, so if we're going to try to do this, you know, how do we get there?
So how do we get there? You know, kind of a beginning to that, the fun fact, so slide 6. If you've ever been to Johnson Space Center or ever been to Huntsville or the Kennedy Space Center, you've seen a rocket like this on the lawn that looks like a cool lawn ornament. But these are actually the Apollo spacecraft that would have been used in Apollo 18, 19, and 20.
Huh.
Now this technology is gone, although, you know, in theory, if you filled it full of rocket fuel, you could go back to the moon, but it's been sitting out for 40 years. So we need something else to get there. So there are 2 components. One is this space launch system that's a heritage between a little bit of the shuttle parts. So you'll notice on this, the external rocket boosters on the side are shuttle heritage, but also the Apollo heritage, that main stack of rockets is, you know, Apollo era with the shuttle rockets being the actual booster. And this, you know, right now the United States doesn't have a way to get into space. We're relying on the Russian spacecraft to get us there. We know, or we hope, that very soon, you know, with the Dragon rocket, we'll be able to get to space station, kind of, you know, through using private means, which will be great. So this allows us to take it to the next capability, build this SLS rocket system, and be able to take humans, you know, anywhere we want in the solar system. It's going to be sort of a slow process. The first launch of humans is, you know, about 2020 to go, you know, just probably beyond the moon, maybe rendezvous with an asteroid, and then 2025 with the bigger spacecraft to get even further. And also kind of as a Apollo component is this Orion spacecraft slide. So this is being tested now. It's, you know, done a couple laps around Earth on a rocket. And this will hold, you know, 4 to 6 astronauts. So it's a little bit more roomier than the 3 astronaut Apollo configuration. But still, you know, if you're going to go on to Mars, it's going to be tight. So there needs to be another kind of crew system built beyond that will actually give some livability, some habitability space like ISS or International Space Station, so that, you know, the crew doesn't keep tripping over each other.
Right, because that's a non-trivial journey to Mars.
Yeah, you know, it's going to take us at least 9 months to get there, and, you know, 9 months back, and, you know, probably a year on the ground. So you're 3 years kind of, you know,
You know, the same three friends.
He is with the same three friends. And one of the great things about going back to the moon is learning how to live off the Earth. You know, we do have experience with the International Space Station. We have, you know, a little bit of experience with Apollo living on another planet. But, you know, space is a harsh place.
Yeah.
You've got radiation from cosmic rays from outside our solar system, the solar wind, and you know, the solar storms that can happen that, you know, affect electronics here on Earth. If you're in a spacecraft on your way to Mars and get hit one of those, not only will your electronics be damaged, you know, it could also damage the humans on board,
Right.
catastrophically. So we need to have that space on the moon to see about shielding and, you know, how livable are those conditions?
Yeah, yeah, that could be a practice run, as it were. But the moon is close enough that you could get back.
You could get back.
Much more easily if you needed to.
Definitely. It's only about 3 days away by rocket,
Right.
so you know you can easily come back to the safety of home. And you also get to try the in situ resource utilization. So we know there are these ice pockets at the polar regions, and on Mars, similarly, there's, you know, icy permafrost regolith. So, you know, one of the commonalities is being able to take that material, heat it up, get the water, the gases, so that you can have your drinking water.
Right.
You can have the water break it into oxygen for breathing, or you can take it as hydrogen, and that's your rocket fuel that you can mix with oxygen and go to other places in the solar system.
Right, because then the water is a very key component, right? Because water, of course, we need it.
Yes.
Well, all these space systems are very good about recycling water. There is loss all the time when you recycle it.
Right.
And so you need it on a longish journey you need to have a source to replenish it.
Right, and you know, not only that is, even just taking it off Earth is a huge energy penalty. You know, every, you know, pound that you take is worth its weight in gold. So if you can fuel up at the moon with your water, the energy penalty is a lot less, like 90% less.
Sure, right.
So you could just fill up there for the water that you need for the journey, and then go on, and not have to lift all that and have either multiple spacecraft launches or, you know, an extremely huge spacecraft.
Yeah, well, that's I hadn't thought about that, but again, that's a great reason to do it. Right? You should be able to design a craft much differently if it was going to stop and refuel, basically.
Yeah.
Excellent, excellent. So let's see, where are we going next then on this?
Well, you know, we've talked about practice lunar bases, and you know, we also have had practice lunar bases right here in Hawaii.
That's right.
And they're, you know, really studying. So this is the High Seas program. A professor at UH is one of the PIs on that, and they're doing these long duration. You know, they're currently in one now. They just started a month ago of a year long. You know, about 6 people in this habitat, which, while roomy, you know, you have that dynamics of people interacting without any outside contact, except for, you know, the voice, for a whole year. They've done it for, you know, different amounts of time for, you know, 1 month, 4 months, 6 months. So now it's going to be a full-on year, and it gives us that, okay, you know, how do you pick people who are the best for socializing in such an enclosed environment?
Yeah, because no, I hadn't realized that. If they're really trying to, there are people in there now who have volunteered, basically.
Yeah,
stay
yeah,
there a year.
yeah.
And unless they get desperately ill, they're going to be there for a year.
Exactly. You know, hopefully all goes well, and you know, about 11 months' time, they'll be coming out all happy and, you know, healthy. And from that, there will be a lot of science research about, you know,
The psychology.
of how that works, and you know, to even how you plan the different setups. You know, right now it's in a dome with 2 floors. They have the sleeping quarters up top, and then the living quarters down below. And they go out and they do, you know, sorties or extravehicular activities, and you know, do some sampling, some science, and you know, it's that measure of how much science you can do, how much you're just trying to stay alive, and how much, you know, can everyone get along and play nicely.
Well, plus there's, of course, the real health issues, right? Of being in a low gravity, high radiation environment for really prolonged times.
Yeah, so that's where the moon will, you know, it's not, you know, the quite zero gravity, it's a 1/6 lower, but it does give you that, you know, indication, okay, you know, here are some things, you know, we still don't have the bone density going down and other problems, you know, a loss of eyesight, not going blind, but you know, start to lose some of your 20/20 vision. And sometimes it comes back, and sometimes it doesn't come back to being perfect. So these are things we have to figure out medical means of being able to overcome, so that when people get to Mars, it's not, they're just laying there. Yeah, we can't move. Our muscles have atrophied. So, they're coming up with ways to do that. But I think we can, start at the moon first.
Excellent. We'll come back and look some more at some of these issues here. You're on research in Manoa. Dr. Jeff Gillis-Davis here from HIGP, and I'm your host, Ethan Allen. We'll be right back.
Hi, I'm Donna Blanchard. I'm the host of Center Stage here on ThinkTech Hawaii. Center Stage airs every Wednesday at 2 o'clock, and of course you can check out our archives on YouTube or on ThinkTech Hawaii anytime you like. Why should you do that? Because this is an arts show that I believe is making a difference in lives. We talk with artists of various ilk. We talk with painters and writers, playwrights, novelists, poets, sculptors, dancers, you name it, directors, actors, of course. And we don't only talk about what people do, but we talk about how they do it. And my favorite part of the conversation, we talk about why they do it. And it's really common on this show to hear people say, wow, I didn't think about it that way. And it's very common to hear people afterwards who have seen the show say the same thing. And I hear all the time that people are inspired by the conversations that we have. So why don't you join us and be inspired too? That's Center Stage on Wednesdays at 2 o'clock. We'll see you Center Stage.
And you're back here on on Research in Manoa with me, your guest host, Ethan Allen, filling in for Jay Fidel. With me today in the ThinkTech studios is Jeffrey Gillis-Davis from HIGP. We're talking about lunar bases and space exploration in general. So we were talking earlier about some evidence that suggests that there is water on the moon, and you pointed out there's now actually pretty good evidence from several different sources. And I think we have an image here that shows some of that.
So yeah, this shows the moon both at the daytime temperature, that's the red globe, and then the blue or purple one is the nighttime temperature to show the extremes. So you're going up from about 300 degrees Fahrenheit down to about 300 degrees, minus 300 degrees Fahrenheit. So you can see at the equatorial regions, it's a big swing. But at the polar regions, it's a much lower swing of temperature.
Right, they're much closer in color, but basically.
Yeah, exactly. And that's because the moon is situated where its rotation axis is pretty much perpendicular to the ecliptic plane or the direction the light's coming from the sun. Versus everyone learns in school that Earth is tilted at 23.5 degrees, which gives us our seasons.
Right, the moon's only tilted a degree or two?
It's not even, it's like a half degree.
Okay.
So on the polar regions of the moon, or for the moon, you wouldn't have seasons. And those polar regions, if you have a mountain, as I mentioned before, you could be in eternal sunlight. Or if you have a crater, and the moon has lots of craters, you're in permanent shadow. And the next slide shows that the temperatures there in those permanently shadowed regions, and this data is from the Lunar Reconnaissance Orbiter Diviner Imager, so it actually measures temperature. And you can see in those purples and blues, you're at, like minus 350 degrees Fahrenheit. And what happens is, these molecules that are what we call volatile bounce around the surface of the moon, but they hit one of these cold traps. They're extremely cold and the molecule sticks. And then, another water molecule or, other volatile gets in there and sticks and accumulates over a long period of time. Now, one of the big questions we have is, well, what's the state of this? Is this, a big ice cube?
Right.
Is it dirt on top of the ice cube? Is it ice and dirt all mixed together? And what other volatiles are there? We saw from L-Cross that there are other volatiles there as well. So what we want to know is we want to be able to go out and measure them. How much is there, what percentage, and how easy would it be able to extract? Some basic mining reconnaissance stuff.
Right, because if you're going to use it for the refueling that we spoke about, you've got to know
how much is there,
right, and how to process it.
And how to process it.
It's one thing if it's all pure water. It's a different thing if it's water and dirt.
Exactly, and that might change the game if there's
Right.
a huge energy penalty for converting it into water and it's easier to lift off the Earth. I don't think that's the case, but it is a consideration that we will have once we get to these cold places and do some basic mining.
That's intriguing. There are a lot of very interesting science to be faced by the people up there. And then when you get people established there, what's the best way to get that to make use of those resources, right?
Right. So once if you want to go down and look at this material, you're going to go down into a very cold region. So the rover that you make is going to have to withstand that very cold temperature, and things can get brittle.
Right, can't stall out.
Yeah, can't stall out. So coming over that technology, and that's one of the things. I think the last slide that I have shows. Oops. Oh, so this is the L-cross impact. So this is what happened in like 2010. This is what they call the shepherding spacecraft, the part of the spacecraft that's closest to the screen, and then you see the flash of the actual upper stage that hit into the moon. It was something like the size of a bus, and it measured the composition of the material coming out and showed that it had some water in it. This is from, again, the Lunar Reconnaissance Orbiter, but this is the LEND, or neutron spectrometer measurements. And it shows in the blues and purples, the North Pole is on the left and the South Pole is at the right. It shows the distributions of the hydrogen in these polar regions. And the estimates are between about 0.2 to 0.5% water. So heating that up and being able to get the water off will be great, and it's the next step we need to do. And then here in Hawaii, they've actually started to test one of these new missions that they hope to launch, a resource prospector, which the part on the right is the lander part. So that would land in maybe one of these permanently sunlit regions and be able to talk with Earth and be able to also talk with the roving spacecraft. And then that rover spacecraft, which has a number of instruments on it, would go down and assay the material that's there, and what kind of level or percentage of water is there, how hard is it to extract, how extensive it actually is. And then feed that back to us so that we can calculate.
Right, but that needs to be a very hardy little vehicle, because some of the shift there looks like in those craters is very abrupt.
It is.
You're on one side and you're just baking in the sun, and you drop the other side and
you're instantly freezing.
Yeah.
So one of the things that needs to be overcome is it's going to have some kind of internal heat source and energy source. So having some kind of thermonuclear energy source inside of it, which we have had in different spacecraft in the past, Voyager, Cassini. So the technology is there, but it is starting to go away. It's harder and harder to get these, what are called RTGs, or the next generation of RTGs. But it's going to have something like that in order to survive that cold and be able to not take any sunlight.
Right. Yeah. The cold and the heat both present interesting challenges.
Yeah.
To operate in both environments effectively but you probably do want to do that if you're gathering up this ice or icy debris. One of the simplest things it would seem to do is to bring it up and put it out in the sunny side, right?
Yeah. Or even you sit there with a mirror. So you don't even have to go in. It's if you in theory put a mirror on the material, it might start outgassing, and from there you would just have to find a way to capture the outgas. But that would allow you to potentially also look into these very they're permanently shadowed, so there's no light in there to take a camera and take a picture unless you have a kind of the flash, and that taking a mirror and shining around might be kind of the simplest things to do.
Interesting. That seems like an intriguing way to do it. And so, what's your best guess as to time frame on this?
That's kind of tough. Unfortunately, right now, the moon really isn't favored with NASA going back with humans. So to go back there, we'll have to take some kind of change in philosophy. Right now, the major goal is to go on to Mars or to go on to even asteroids. But the moon doesn't seem to be the most important place in the space to go with people. So that philosophy will have to change, but hopefully by the mid-2020s, we'll be able to get back with people, demonstrate that this is a needed technology or a needed resource for NASA, for the U.S., for maybe a global partnership of spacefaring nations to use this resource to make us a truly spacefaring country or world to get around to the solar system, because it's our fuel station, our fuel depot to do that.
Right. Well, plus the moon gives you then a vantage point on Earth, right? That you can set up sophisticated but stable instrumentation there, right? And really do a lot of kinds of observations that you probably can't really do from spacecraft, right?
Well, you could do the same things probably from spacecraft, but spacecraft, need to be refueled. They, may go bad. If you have something on the moon and people right there to either fix it or upgrade it, it is, kind of the best place to be in that respect. It doesn't take any energy to really just be there. So that's a great advantage. The other advantage is that if you go onto the far side of the moon, you can do radio astronomy and do it in a way you can't do it here because of all the radio noise that Earth puts off. Being on the far side would give you another advantage to, use that shadow to, look at the universe in radio wavelengths like never before.
Huh, interesting. That of course, it has a very different set of challenges to set up a base over there.
Yeah. But, it can be done. It wouldn't be maybe the first thing we do, but, in the timeline of things. Other possible things are the moon could serve as an equitable space for sending solar energy back to places on Earth that, can't afford setting up solar panels or don't have electricity. It could actually collect solar energy, beam it back to Earth in places that don't have any power with a simple collector, and allow them the equability of having electricity so that people can do homework at night or work at night, simple pleasures like that.
Excellent. Well, that's a lot of options, it seems like.
There are a lot of benefits, and it I think once considered will be what leads us back to going to the moon.
Mm-hmm. So a lot of this though depends on these small steps that are being taken right now, right? This habitat you were describing earlier, that experiment more or less has to work, right? And people have to be able to get along and survive together for a prolonged period.
Right, and that's even more so for Mars. But if it does fail, failure is an option sometimes. As long as you learn from that failure, okay, what did we do wrong, and what do we need to do different in the next step? And I think again, that's something the moon will show us once we're off the Earth, and there will be things we don't consider about living in space on a different planet. Oh, we need to set up things differently because we're in a different place. Mm-hmm. And if you're on Mars, it will be potentially a lot more difficult to redirect what you need to fix.
Sure.
It'd be better to have as much experience living off the Earth before you go to Mars, rather than try and accumulate that by going just to Mars.
Right. No, as you said, it's sort of like it's in our backyard. It's a quick, easy overnight camp out, as it were,
yeah,
relative to making the jaunt to Mars.
Mm-hmm.
And so, yeah, you could fix things. You could do multiple visits. You could,
you could come back easily if an emergency happened.
Right.
Yeah.
Send up extra supplies if need be.
Yep.
As long as you set things up properly. Whereas, on Mars, you pretty much you're going there one shot, and that's basically going to be it.
Fingers crossed.
Indeed. So.
But in that same time, they could be setting up all these extra science benefits and global benefits, sending power back, even just maintaining a constant view of Earth to see how it changes. Landsat has done that, for the last 30 to 40 years. This could even extend that beyond that to see how Earth is changing over time.
Yeah, excellent. Sounds like there's many benefits to this. It sounds like some great work ahead, very exciting science that will hopefully lead to better lives for us all here.
I hope so.
Well, excellent. Thank you so much, Jeff. I've really enjoyed chatting with you here. I've learned a ton, and it's great to explore this region here.
Well, thank you, Ethan. It's been great talking with you.
Okay, aloha.
Aloha.